What we've been looking at so far in differential equations, I'm not sure if you guys have realized this, it's a little different from, pre-calculus and calculus, where a lot of times, maybe like in other courses, you're solving for a variable. In differential equations, you're learning how to solve not for a variable, you're learning how to really solve for an equation. It's a little bit of a different idea, but there are some similarities here for sure. And we've been looking at a lot of different equations so far. We've been looking at just some basic linear, we're looking at some quadratics or, second order differential equations. And we're seeing how Laplace transformations can be very, very useful as it allows us to curtail a lot of the complexities that you would find with differential equations in calculus. And it sends it into the algebraic realm, where you're looking at polynomials, you're looking at rational functions, and then you're basically no longer doing really much of calculus, you're doing a bunch of pre-calculus. Partial fraction decomposition, working in that realm. Then you send it right back to the sender, and you work, back in the calculus realm. Okay, so that's a lot of what Laplace transformations do. They're very, very useful for lots of different applications, and they're also useful as we saw with stuff with step functions. The step functions, they're not continuous. Would you say? They definitely have those steps. And you can definitely take those steps and really start layering them on top of one another. And you can really make some really interesting functions where it goes up a little higher and a little bit lower. And you can do all kinds of things like this by using the step function or the Heaviside function. And we also saw a little bit about that, the delta function, basically where you get that big old impulse where you just basically smash it at some particular value and it spikes. Okay, that's also very interesting, but again, that's not necessarily really continuous. And there's a lot of functions out there. We do work with continuous functions. And when we're integrating, okay, we probably want to talk about functions which are continuous, but there are functions out there which are really not continuous, such as sequences. Where a sequence is really just a discrete function whose domain is going to be over the integers. And a sequence, sequence that you probably really, really know, or a sequence that you're really familiar with, is the Fibonacci sequence, where you're looking at 1 and 1. And you add up the next two values, you get a value of 2, then you get 1 and 2 gets you a value of 3, and 2 and 3 gets you a value of 5, and then you get a value of 8, and then so on and so forth. And the Fibonacci numbers, the sequence, has been around for hundreds and hundreds of years. I think it started off with something with rabbits. They get married and they have little rabbits. They grew up and they also have marriages. And they also have little rabbits. That's how this game got started, with pairs of rabbits. One pair, two pair. And then it kind of grows pretty big, like you're breeding a bunch of rabbits. Okay, but the Fibonacci numbers, the internal structure for it is you can write it as a sub n plus 2, a sub n plus 1 plus a sub n. And here's kind of the deal. This is not the Fibonacci numbers. This is just a framework that's going to generate the Fibonacci numbers, provided that you have certain seed values. Because guys, if I was to say A0 and A1, they're both 0, what sequence am I going to be generating? 0, 0, 0, 0, 0, 0, 0, 0. A bunch of zeros. That's not that sequence. You need to have the structure, but you also need to have the seed values. And the seed values, these initial conditions, things like A0, you can maybe start it off at 0 if you really wanted to. And A sub 1 maybe starts off with a value of 1. You start feeding that through the system, through the recursion, through the protocols. Okay, you're going to get 0 and 1, and then it takes off thereafter. Fibonacci numbers, they're very useful. They come up in a lot of different places. And one such place is in your anatomy. If you look at your bone structure, you do have the Fibonacci numbers encoded within your bone structure. You got 1 digit, 2, then 3. You also have it right here in terms of your ear. And the way you would see it in terms of the ear is you look at this spiral. And probably one of my favorite examples, illustrations of the Fibonacci numbers, is you take 2 blocks, unit blocks, put them next to each other, and then from here up top, put a 2 by 2 block, and on the side, you put a 3 by 3 block, And then down below, you're going to put a 5 by 5 block. I'm kind of a bad drawer, but yeah, that's a 5 by 5 block. And over here, okay, you're going to get a 8 by 8, and you keep going around in this process. And if you were to connect up and make a spiral, that right there is what you're going to see right here in your ear. So quite literally, you are encoded with the Fibonacci numbers. Man, aren't you kind of glad that an accident happened? Or was it by design? Probably by design, right? Really interesting when you start seeing all these fingerprints kind of sprinkled all throughout. But again, Fibonacci numbers, you see them in a lot of different places. And we can really talk about a lot of applications. There's a journal article out there, or journal known as the Fibonacci Quarterly. And all it really do is talk about Fibonacci numbers. That comes out quarterly, so 4 times a year. It's just not this, but there's a lot of things with this. Pascal's triangle has the Fibonacci numbers in it. Binomial coefficients have the Fibonacci numbers in it. And there's a lot of other things out there which have the Fibonacci numbers within it. And one of the things you do talk about in programming is, hey, let's calculate the 100th Fibonacci number. And what they're trying to do is set you up for failure when they say that, because they know if you were to program this recursively, you're going to have a lot of overhead, and you're going to draw on too much system resources, and it's going to crash the system, which it should, because when you do recursive programming, that's what happens. But if you can find a way to work around those complexities, you can actually figure out the 100 Fibonacci number, the 200 Fibonacci number very quickly by finding what's called a closed form. And if you can find a closed form, that's just a fancy way of saying, hey, let's find a formula. If you plug in the n value, we got it. And what I'd like to do here today is take a little closer look at the Fibonacci numbers, the sequence, and how we can actually find a closed form. But here's kind of the problem. When you're looking at a discrete sequence, sequence like we have, it's not continuous. Things are going to break down really, really quickly. So what we're going to need to do is define a special type of function. And this function, we're going to call it, we'll say y sub t. And y sub t is going to correspond to a sub n, provided that you're on this particular region. Okay, so notice how closed, then it's open. So in other words, if you're looking at an interval, n is going to be an integer, so we're going to start off at 0, then 1, then 2. So the first interval is going to be right here at 0, and it goes up to 1. Then it's going to pick up, we're going to close that interval, which was open, so we're going to close it back up, and then go to 1 to 2. Then we're going to close that up, so now it's going to go from 2 to 3, and we're going to go all the way down. And while you're on this region right here, you are taking the value of y sub t, which is going to be nothing more than a naught. And right here is going to be a1. And right here, a2. And then so on and so forth. So basically, guys, what I'm generating here when I'm looking at this protocol is just another way of looking at your step functions. When you're looking from 0 to 1, maybe you're right here, a0. And then from 1 to 2, maybe it's going to be a little higher, or wherever it's going to correspond to, but you're going to close it up, and then you're going to have this. Okay, and what I want to do is just kind of look to see what's going on with these step functions in terms of, I need something that's a little bit more continuous, something like this, as versus just looking at a bunch of dots for discrete, because we're working with derivatives, we're working with integrals, and we need some aspects of continuity. So the very first thing is, whenever you're looking at the function y of t, and you want to take this Laplace transformation, it's going to be exactly the way you would think it's going to be. And we can still take this just being f, where, again, this is a function in terms of s, so it's the same step we've been doing thus far. But there are some other things, some other liberties that we could definitely take here. And I just want to kind of show you some of these things that we can do. Oh, this should be positive infinity. But we can start invoking the ideas that we know back from Calculus 1 in terms of integration, where you can take an integral. If it's a well-behaved integral, and these things are definitely tapering off to 0. That's why you need this exponential that's going to send it down 0 very quickly, so you're going to be okay. But you could, take things from 0 to 2, for instance. You can take the integral, go from 0 to 1, and then go from 1 to 2. Okay, well, I can do that from 0 to positive infinity, where I can say 0 to 1, and then I'll say 1 to 2, then 2 to 3, and then 3 to 4, so on and so forth. Now, for each one of these pieces, let me just write it a little differently. I'll say n plus 1. That's going to be representative. This integral, this one, and this one. And we are looking at y of t e minus st dt. When you're on the interval from n to n plus 1, the y function is defined as the sequence value, the a sub n. So that is awesome, because what that allows you to do is to say, well, I'm on the interval that's a sub n. And you're integrating with respect to what variable? Not n. So what's that? Constant. That same trick we did the other day. Take this, factor it out, where beforehand, okay, impossible to solve because you don't know what's going on with y. Possible to solve because I know how to integrate an exponential. Do a quick U sub, fundamental theorem of calculus, properties of exponents. Same thing here as it is there. Factor it out, and you'll be left with e to the minus s minus 1 over negative s. So that's what's going to happen for each and every single one of these integrals. And what we're doing is we're summing them up. And you can do some other things as well, such as n's changing, not s, so that's called a constant. Take it and factor it out. Okay, it is over minus s. Okay, so you can also just take it and recalibrate it. And there's kind of the idea. Okay, you could, when you're looking at these step functions, okay, take the Laplace transformation and you're going to generate this function right here. And here you got some kind of rectangular pulse function. Over here, you get something called like a z transformation. But okay, really, just think about, we just have a series and we got the Laplace transformation. Okay, well, when you're working with recursions, such as the Fibonacci numbers, you're going to have something like an a sub n, but look what this is. A sub n plus 1. And what that refers to is one step over. And if it's a sub n plus 2, it's 2 steps over. So I also want to consider what's going to occur when we're looking at a composition. Okay, so what is the Laplace transformation of y of t plus 1? And y of t plus 1, that's going to correspond to that. Okay, so once again, we can apply the definition. And one thing you can do is do a U substitution. What if you set equal to t plus 1? Under this protocol, okay, you're integrating in terms of t. I'm now going to be integrating in terms of u. Drop them to 0. Lower bound to 1. And if t is going off towards positive infinity, so is u. Okay, you're going to have y of u, and you're going to have an exponential minus s, and then you have to convert everything over. Now, let me tell you right now, this is not in the text. So you're going to have u minus 1, that's your t. Do a little properties of exponents. I would say that's a little sus, but I'm too old for that. But I do see an e to the s. I can factor that out. But look at this. That looks pretty close to something, doesn't it? What if we started off at 0 as opposed to starting off at 1? Then you would have that. Okay, so here's what we can do. I know it's going to correspond to e to the s, 1 to positive infinity, and we'll have our integrand. Start it from 0, run up to positive infinity. Then chop a little bit off the top, okay, or maybe a little bit from below, 0 to 1. Can you see it? Okay, if you're going from 0 to positive infinity, and you say, well, I really didn't want the first part from 0 to 1, what would you get? 1 to positive infinity. And this right here, guys, that's F. This right here, you're integrating from 0 to 1, and on the region, okay, we're not worried what's going to happen at the value of 1, because due to the definition of the step function, we're just really seeing what's happening at the lower bound part. This, when you're on the region from 0 to 1, this function is always going to correspond to A0. Factor it out, because it is a constant. Okay, drop in the 1, drop in the 0. And you can clean up a little bit more. Of course, that's going to correspond to minus 1. And then you take the negative if you want, absorb it up top, rewrite it. Okay, so here's what happens. Okay. You can try this out later on, but what you're going to come up with is e to the 2s times f. You're going to have e to the s over s, 1 minus e to the minus s. And do pay attention right here. It is a negative exponent. Sometimes there are going to be positive exponents. If you wanted to, you can push the e to the s through, and we'll get you 1 here and e to the s here. But it's just my way of looking at it. Okay, and you're going to pick up this piece in the back. You're going to have A0 e to the s plus A1. Dot, dot, dot. Math magic. You gotta love that math magic. So here's the process. First thing is, you want to take your recursive relationship and redefine it. Okay, so redefine the recurrence relation in terms of these step functions. Okay, and do note the bounds. Okay, that's less than or equal to, and that's going to be less than. So you're going to include in, but you're going to keep n plus 1 open. So whenever you start overlaying them, you're not going to have any contradictions. Okay, so you're going to redefine. Make sure I get that right. Redefine the recursive relationship like this. Next, you're going to take the Laplace transform, and you're going to apply these identities. Okay, what's going to happen here? Y sub t plus 1, y sub t plus 2. And if it's a third order recursion, we're going to add one more piece to the mix, y sub t plus 3. But for our purposes, we're just going to mostly just focus on what's happening here with maybe like a second order. Okay, and the next thing is you're going to solve for f of s. Like we have been doing thus far with the Laplace transformations. Take the Laplace transformation with some kind of equation, you figure out the capital F, and then you solve for it. And the next thing, what we're going to do here is a slight little difference, is we're going to go ahead and set r equal to e to the s. And all this is going to do, this is going to help us to unlock it a little bit easier so we can see things. And we're not going to really convert everything over in terms of r, and you'll see why here in a moment. But I'm going to use this to help me to make some observations. And this is just to better see some polynomials, rational functions, so that whenever I have a polynomial or rational function, I might want to do partial fractions decomposition. Okay, and then 6, we're going to use this identity, where we're going to look at the Laplace transformation. We're going to look at r. We'll take what's called the floor of t. Now, that's just a way just to say, hey, look, when you're taking the floor of t, you have 2.1, it means round down. Okay. If you have 2.9, what that means is round down to the floor. Okay. Versus what's called the ceiling, you never guess why they call it the ceiling. Round up. So if it was a ceiling at 2.9, you would say 3. And if it's 2.1, you say 3. You round up. Okay. The reason why I'm just invoking this is this makes it a little more airtight. But again, just remember how we're defining. We're taking t between n and n plus 1, not including, so I don't want to include that. We really are rounding down. And what you're going to get here, going through the whole entire process, you will get this identity. Okay, so what we have here is just really the setup. We got the tools now. We have the impact driver and the wrench. We can really put some power to these problems, okay, using Laplace transformations in a very, very interesting way. So let's go back to the Fibonacci numbers. And the way that I'm going to calibrate these is I'm going to say A naught's going to start off at 0, and then A1's going to start off at 1, and then it's going to take off afterwards. Sometimes when looking at Fibonacci numbers, you might see someone starting off at 1 as opposed to 0. It doesn't really matter so much. You're still generating the sequence of primary importance. What's really important, though, is make sure you have the structure, because without the structure, it doesn't matter what your initial conditions are. But the initial conditions, they are important, because if you don't have those, even if you have the structure, you can still generate a different sequence. So you just got to be a little careful. So the first step is I want to go ahead and take this, and I just call it y. And without really realizing it, when you're doing this kind of process, you're basically taking the problem, which is in the discrete realm, and you're throwing it into the continuous realm, or maybe some kind of broken continuity, where we can start operating on the functions. Okay, otherwise, we can't operate on discrete functions. Next thing, take the Laplace transformation. And luckily, we already did the heavy lifting. I know what this is every single. It's going to be these identities right here. So I'm going to take this identity, drop it in, and take this one, drop it in, as well as this one. And after I do that, solve for f. Okay, anyways, guys. Apply the Laplace transformation. You have this part, and this part. collect all the s, put them all together. Okay, you got this one. This one you would distribute. And this one you would just pull over. Okay. Now, this might be a really good time to apply the initial conditions. This can help reduce complexity down. And look what we have. Oh, I'm so grateful for this. Look at this. Oh, don't have anything there. Zero. I'm loving that. Right here. That's going to correspond to 1. Okay, so all this is then, we kick it to the other side, e to the s over s, 1 minus e minus s, a1. That's kind of nice. Anything else? Okay, this part zeroed out. That was 1. Distribute it. So it's like having this. That was away. I already moved this over to the left. Looks like that's about it. Okay, now the next thing again, solve for capital F. This exponential e to the s over s, I'm going to just pull out, as well as this piece. And the a1, we'll just call that 1 because that is what it is. Now, this is where the next step comes into focus. Okay, set r equal to e to the s. And what that's going to allow us to do is to reimagine what this is. Where it becomes a lot more obvious. This is where you want to do partial fractions decomposition. I don't really have to push this thing through, and I don't want to push it through for one simple reason. I'm going to use it here in a moment. Okay, so I want to keep that floating around. So, I got to factor this. I got to find the roots. I do know it's linear, so I know it's going to split. Or excuse me, quadratic's going to split into 2 linear terms. And I'm just going to say alpha and beta because it's going to get very complicated more than it already is. If you want to solve, what you're going to find out here is alpha and beta. Use the quadratic formula, 1 plus root 5 over 2, 1 minus root 5 over 2. Now, when you take this and you split partial fraction decomposition, the way that this thing's always going to work so it's always going to split like this. Okay, if you were to put the fractions back together, you would have negative beta plus alpha. So you have to balance it out. Just like that. And alpha minus beta, if you take the difference here, 1/2 goes away. And so really interesting coefficients we have, what are known as these golden ratios. Okay, but what you're going to come up with in the very end, root 5. Okay, now the next part here is after you do the whole entire partial fraction decomposition, this again is really nothing more than e to the s. That was a substitution we used to see the partial fractions a little easier. The next thing is take this part, kind of push it through, so that you can generate this part You're going to see the S, and you're also going to see this. Okay, because remember what I said a moment ago? Pay attention to the exponent. Sometimes it will be positive, sometimes it's going to be negative. So I just need to recalibrate this so it fits precisely. So this part is this part right here is this part. Okay, and the next thing is we do have the e to the s. Push it. Finally, use identity. Take the inverse Laplace transformation. Okay, I'm just going to keep it as alpha minus beta. But again, linear operator, get your y of t. You take the inverse for this piece and for this piece. That's exactly what this piece is right here. Apply the identity. There's r. And if that's r is a little confusing, if it's confusing this r, call it something else, call it c if you want. So you're going to basically take the power of alpha, subtract it off, there's a minus sign, the power of beta. Where alpha and beta, they're defined like such. And guys, right here, this is the closed form for the Fibonacci numbers. So you do not have to go through all the hustle and bustle, going through the recursive operations. If you know the identity, you can calculate the 100 Fibonacci number relatively quickly. Your machine's not going to crash. But try it out. See if this formula actually does work. It will, but see if it works anyways. Now, there's really something else that's being played behind the scene, and this is something called a linear recursion. But there's really nothing that's going to prohibit me in the setup from maybe doing some other things, which may not be so linear. I mean, I can possibly maybe start looking down those avenues, which we're not, but we possibly could. But again, whenever I start talking about linear recursions, it makes me think of linear systems. But if you think of linear operators, and I'm thinking about a linear operator, I can do all this with a matrix a whole lot faster. Matrices are very, very powerful. And we'll talk about this again in linear algebra of how you can actually find this a lot faster and a lot quicker. And what these things right here, they're referred to as eigenvalues. But what this shows you here today is when you're looking at Laplace transformations, guys, they're very useful. They're useful for solving systems of equations or just basic equations, but you can also use them for solving sequences like we did over here. Okay, you guys have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.